the principles of electrical stimulation. First things first, there are some prefixes that would be helpful to know. First, there is a lowercase m, which is the prefix for milli, or 1/1000th. Another prefix that is helpful is the Greek letter mu, which is represented by the character that looks similar to a U with a little extra squiggle on the front end of the U. Mu can also be represented by an uppercase M. Mu is the 12th letter of the Greek alphabet. Mu is the prefix for micro, or 1/1,000,000th. These two prefixes are commonly used in units of measurement for electrical therapy. You may see them frequently within the context of this information. All matter is composed of atoms containing ions. An electron is a negatively charged ion. There is a potential difference, which is an imbalance in the number of electrons at 2 points. The electrical current is the net movement of electrons. These electrons flow from high concentrations to areas of low concentrations in order to equalize the difference. There are numerous definitions of electricity that can be found. Here are 4 definitions. All are correct, but each one emphasizes a different aspect of electricity. Number 1, a property of certain fundamental particles of all matter that have a force field associated with them, manifested by either an accumulation of or an absence of electrons on an atom or a body. Number 2, a form of energy associated with the existence and interaction of electrical charge, manifested by the accumulation of or absence of electrons on an atom or a body. Examples include magnetic or electromagnetic, chemical, mechanical, or electrokinetic and thermal properties. Number 3, a form of energy that exhibits magnetic, chemical, mechanical, and thermal effects, formed from the interaction of positive and negative charges. And lastly, number 4, the physical phenomena associated with the existence and interaction of electrical charge, either static charges, electrostatic, or moving streams of charges, also known as a current. There are 2 types of electricity, static and current. Static electricity is frictional electricity, created by rubbing 2 objects together. In the process, one object gains electrons and the other object loses electrons. An example of static electricity occurs when you rub a balloon on your hair. Static electricity can be stored in an insulated conductor in which the charges are in a state of tension, ready to flow. The discharge is often a single discharge, into the ground or through something else and into the ground. The body of Earth is considered to be an electrical sink, which means that it can accept or supply any reasonable amount of charge without changing its electrical characteristics. Current electricity is characterized by a stream of loose electrons passing along a conductor. Current passes in one of 2 ways and is therefore named after its method of moving along a conductor, either direct current or alternating current. As can be seen in the picture on the slide, electricity has a negative and a positive pole. The negative pole is called the cathode and is an area of electron concentration. The positive pole is called an anode and is in an area of low electron concentration. In certain forms of energy, the polarity matters as electrical current is flowing in only one direction. We can see this in the 2 circles and also on the patient in the middle of the slide, who has 2 electrodes on her shoulder. The arrow represents the movement of the electrons. Electrons like to flow from areas of high concentration to areas of low concentration, or from the cathode to the anode. In other forms of electrical current, such as alternating current, The poles switch from positive to negative during the electrical charge. In order for electricity to be functional, a circuit must be completed. When the circuit is open, there is an incomplete pathway and the electricity is unable to flow. Think about a light switch. When you flip the light switch, usually in the down direction, the circuit is open and does not allow for electricity to flow to the light, and therefore the light stays turned off. When a circuit is closed, there is a complete pathway between two poles. When you flip the light switch in the opposite direction, usually up, the light comes on. Behind the walls, the electrical circuit is closed by flipping the switch, and the light comes on as electricity flows along the closed circuit. It is important to understand some of the characteristics of electrical currents. The amplitude of the current is the vertical distance above or below the baseline. The isoelectric point is considered the baseline. This means that it is the point at which there is not a positive or a negative charge within the current. The charge is zero. The pulse duration is also referred to as the wavelength. This is defined as the horizontal distance required to complete the shape of the wave. As has been stated, there are two primary types of electrical current: direct current and alternating current. Direct current is the continuous flow of electrons in a single direction. We can see this with electrodes in the upper right corner of the slide. Direct current is a continuous positive anode and negative cathode polarity throughout the current. Direct current has some distinct features. It is monophasic, which means that the current only has one phase, hence the word mono. This means that the current flows in only one direction. The current is uninterrupted, which means that it is continuously on and the circuit is continuously closed. A term formerly used for this type of current was galvanic current. Alternating current is the continuous flow of electrons that reverses direction periodically. We can see this within the electrodes in the upper right-hand corner of the slide. Alternating current switches from positive to negative polarity throughout the current. It is defined by frequency or cycles per second. Alternating current can be turned off and on to create bursts. Like direct current, alternating current has some distinct features. It is biphasic, which means that there are two phases, hence the first part of the word bi. This means that the current flows in both directions. The current is uninterrupted, which means that it is continuously on and the circuit is continuously closed. A pulsed current has the distinct feature of having an interrupted electron flow. A pulsed current can either be monophasic, having only one phase, or the current flows in only one direction, such as the box current in the upper right-hand corner of the slide, or it can be biphasic, having two phases, or the current flows in both directions, such as the larger current at the bottom of the slide. There are periods of off or no current with a pulsed current. We use pulsed current frequently in rehabilitation, specifically when we are using electrical stimulation to retrain a muscle towards contraction. We have already gone through many aspects of electrical current, but there are several more definitions that we need to explore to better understand electricity. These pulse attributes we will explore in the next slides include phase duration, pulse duration, interpulse interval, intrapulse interval, rate of rise, rate of decay, pulse charge, and pulse frequency. We will start with phase and pulse duration. A phase duration is the amount of time it takes for the current to leave the isoelectric line and return to the isoelectric line. On this slide, the phase duration is represented by the red arrows. The pulse duration is also known as the pulse width. This is the time required for each pulse to complete its cycle. This is usually reported in microseconds or milliseconds. A short pulse duration is a pulse that lasts less than 150 microseconds. A long pulse duration is a pulse that lasts longer than 200 microseconds. The time from the beginning to the conclusion of the final phase is considered the pulse duration. The interpulse interval is the time between successive pulses. This is the time between the conclusion of one pulse and the start of the next. This may be felt as long off periods between bursts of electrical energy. The intrapulse interval are the short off periods within a pulse. The rate of rise is the amount of time from the beginning of a pulse until it reaches maximal amplitude, or the time it takes to get from zero or the isoelectric point to the maximal amplitude within each pulse. The rate of decay is the time from the maximum amplitude to the end of the phase, or the time it takes to get from the peak back to the zero or isoelectric point. The pulse charge is the amount of electrical charge of a single pulse, or this could also be the sum of phase charges. The pulse symmetry is the relationship between the shapes of the two phases of a biphasic pulse. The pulse symmetry could be symmetrical or asymmetrical. A symmetrical pulse is a pulse with identical phases on either side of the line. An asymmetrical pulse is a pulse with different phases on either side of the line. A pulse charge balance is the relationship between the charges of the two phases of a biphasic pulse, independent of the symmetry of the phases. The pulse charge balance could either be balanced or unbalanced. If the pulse charge is balanced, the pulse contains equal phase charges. If the pulse charge is unbalanced, the pulse contains unequal phase charges. This is a picture representing the pulse charge. The pulse on the left-hand portion of the graph represents a balanced and symmetrical biphasic pulse. The pulse on the right-hand portion of the graph represents an unbalanced and asymmetrical biphasic pulse. Pulse frequency is measured in cycles per second. In the world of modalities, we commonly see the pulse frequency measured in hertz, which is abbreviated with a capital H and a lowercase z. An example of pulse frequency modality is microcurrent. It has a pulse frequency of less than 1,000 hertz. An example of a medium pulse frequency modality are interferential and Russian currents. They have a pulse frequency of between 1,000 and 100,000 hertz. An example of a high pulse frequency modality is diathermy. It has a pulse frequency of greater than 100,000 hertz. In modalities, it is common to use a pulsed current. The frequency is measured by the number of pulses per second, or PPS. Some modality settings have what is called a duty cycle. A duty cycle is the percentage of time the current is flowing, also known as the pulse duration, over one pulse period or the total cycle time. Thus, current with an on time of 10 microseconds and an off time of 10 microseconds would have a 50% duty cycle. If we work through the math, we can take the 10 microseconds the machine was on, we divide the 10 microseconds that the machine was on by the total time, the 10 microseconds the machine was on, added to the 10 microseconds that the machine was off, which equals 20 microseconds. So on the third line of math, we see 10 divided by 20 equals 0.5, and we multiply that by 100 to get a percentage. The 0.5 times 100 equals 50% duty cycle. An additional example would be a current with an on time of 10 microseconds and an off time of 40 microseconds. This would have a 20% duty cycle. This slide is a pictorial representation of the pulse attributes we just spent time exploring, including phase duration, pulse duration, interpulse interval, intrapulse interval, rate of rise, rate of decay, pulse charge, and pulse frequency. If we look at a biological process such as a heartbeat, it has an electrical property to it. If we break this electrical pulse down, we see that this pulse is not monophasic, or even biphasic, or even triphasic, meaning it has 3 phases. This is what is called polyphasic electrical impulses, signifying that there are many phases of the signal. This is an example of alternating current. This alternating current is an asymmetrical pulse, meaning that the pulse has different phases. This pulse charge balance is unbalanced, meaning that the pulse contains unequal phase charges. A phase is a period of unidirectional charge particle movement, or current flow. If we examine the number of pulses in one heartbeat, we can see that there are 5 phases. The blue line represents an isoelectric point of the heartbeat. This isoelectric point represents the starting and ending point of the phase. Thus, there are 5 electrical phases in one heartbeat, as represented in the slide. I have drawn lines in red to indicate each time a phase was completed. The phases of a heartbeat can also be divided into sections relating to the shape of the electrical signals produced when viewing the heartbeat via an ECG or an electrocardiogram. This traces the electrical activity of the heart. The wave shape produced is called a QRS wave, with each part of the wave being labeled to help describe what is happening at each stage. The P wave, or atrial systole. The SA node fires and the atria contracts, causing atrial systole, which forces all of the blood into the ventricles, emptying the atria. The QR interval, ending of the ventricular diastole. The AV valves remain open as all remaining blood is squeezed into the ventricles. The electrical impulses from the SA node reaches the AV node, which spreads the signal through the walls of the ventricles via specialized cells called the bundles of His and Purkinje fibers. The R peak is the end of the ventricular diastole and the start of systole. The RS interval, or ventricular systole. As the blood is now all within the ventricles, and so pressure is higher here than in the atria, the AV valves close. The ventricles start to contract, although the pressure is not yet high enough to open the SL valves. The ST segment, or ventricular systole. Pressure increases until it equals aortic pressure when the SL valves open. The blood is ejected into the aorta and pulmonary artery as the ventricles contract. At this time, the atria are in diastole and filling with blood returning from the veins. The T wave, or ventricular diastole, the ventricles relax. The ventricular pressure is once again less than the aortic pressure, and so the SL valves close and the cycle continues. The TP interval, or ventricular diastole. The atria and ventricles are relaxed. Blood is flowing into the atria from the veins. As the atrial pressure increases above that of the ventricle, the AV valves open, allowing blood flowing into the ventricle. Current modulation includes all the manipulating, regulating, and adjusting of the input current to create a variety of specific output waveforms. An example of current modulation is continuous current. A continuous current is one in which the intensity stays the same, or a certain pattern is repeated throughout the course of the treatment. Continuous current is common among electrical currents, but is less common among electrical modalities. Most electrical output is pulsed. A pulse is a finite period of charged particle movement, separated from other pulses for a limited time during which no current flows. A pulse consists of one or more phases, which is a period of unidirectional charged particle movement, also known as current flow. In electrical modalities, this is described as the interrupted current characterized by off periods. Examples of pulsed current are the pulsed biphasic current, which is a low modulated current. This could occur in a burst or ramping series as well, which may be discussed on the next two slides. A burst is a finite series of pulses, or a finite interval of alternating current at a specific frequency, flowing for a limited time period, followed by no current. For example, turning a pulse train or an AC on and off. The pulses are packaged into small clusters and the patterns are repeated at regular intervals. A pulsed current can occur in a ramping modulation, most commonly seen as a gradual increase in intensity. Ramping can either be a ramp up or a ramp down. A ramp up is the time during which the intensity of an electrical surge increases. A ramp down is the time during which the intensity of an electrical surge decreases. Current flow is the result of the interaction of forces, or voltage, and the resistance ohm. The relationship among current, force, and resistance is defined as Ohm's law, which is current, represented by a capital I, is equal to the force or voltage, represented by a capital V, divided by resistance, also known as an ohm, which is represented by a capital R. Another way to think about this is saying current I is directly proportional to voltage V and inversely proportional to resistance R. As resistance increases, more voltage is required to pass the same amount of current through tissues. The electrical charge is determined by a coulomb, which is represented by a capital C. A coulomb is the basic unit of charge produced by 6.25 times 10 to the 18th protons of positive or negative 6.25 times 10 to the 18th electrons negative. Coulomb's law states that like charges repel and the opposite charges attract. A voltage is the force created by an accumulation of or an absence of electrons on an atom or body. The voltage measures the tendency for the current to flow. The measure of a volt is calculated by the amount of work necessary to move 1 coulomb of charge. The current of electricity is a stream of loose electrons passing along a conductor. Current is represented by the capital I and is calculated in amperage, represented by a capital A. The current is the rate at which current flows. It is measured in milliamps or microamps. Resistance is the opposition to current flow. Resistance is measured in ohms and is represented by the symbol above. A conductor permits the free movement of electrons. Some good examples of conductors are metals and electrolyte solutions. An insulator resists the flow of electrons. Some good examples of insulators are air, glass, and wood, as well as other examples. Going back to Ohm's law, please remember that if you know 2 of the factors, the third can be calculated. For example, if you have 6 volts of force and 6,000 ohms of resistance, what is the amperage? Substituting the values of the volts and ohms in the equation above gives I equals 6 volts divided by 6,000 ohms, which equals 0.001 amps or 1 milliamp. Another way to look at this equation would be to calculate for voltage. Voltage equals current multiplied by resistance. Or a third way to use this equation would be to solve for resistance. Resistance equals voltage divided by the current. Unfortunately, there will always be at least some resistance in electrical current, as no current is perfect. There are four major factors to help determine the amount of resistance. 1. The material of the current. Some materials either allow for increased conduction or decreased conduction. For example, metal is a good conductor of electricity, and therefore it is a decrease in resistance, whereas wood is a poor conductor, and therefore there is a large amount of resistance. Number 2, the length of the current. The longer the current is allowed to continue, the less resistance there will be. There is more resistance the shorter the current is, or the more bursts the current has, as each burst has to overcome the resistance of the skin. For example, in an electrical modality, we may try to reach the level of the muscle, and therefore each burst has to overcome the resistance of the skin to reach that level of the muscle. Third, the cross-sectional area that the current is exposed to. The larger the cross-sectional area, the less resistance. The smaller the cross-sectional area, the greater the resistance. And finally, the temperature of the current. The colder the temperature, the greater the resistance. The warmer the temperature, the less resistance of the electrical current. Wattage is the power of a current. 1 watt is the power produced by 1 amperage of current flowing with a force of 1 volt. The calculation is wattage is equal to volts times current. For example, this could be calculated for the power to be used by a device requiring 12 amps from a 120 volt source. If we use the equation voltage multiplied by the current equals the wattage, we would have 120 volts multiplied by 12 amps, resulting in 1,440 watts. There are different types of circuits. We have series circuits and parallel circuits. In a series circuit, there is only one pathway available for travel. If you've ever had a Christmas tree light stand that stopped working because one light bulb burned out, and you have to frustratingly search for that one bad bulb to make the strand work again, then you understand how a series circuit works. If you have ever experienced this, it is because the light strand is using a series circuit. In a parallel circuit, there are multiple pathways available for travel. This means that if one pathway becomes inactive, the lights will continue to work as there are other pathways for that electrical pulse to travel. If we take that Christmas light strand again, that one light that burns out would not stop the rest of the lights from lighting up if a parallel circuit is used rather than a series circuit. So as a practical example, what do you think would happen with biological tissues? Do you think there would be a series circuit or a parallel circuit? Unfortunately, our answer isn't as simple as the Christmas tree light strand example that was previously used. On entering the body, several different electrical paths develop and form a series and parallel circuits. Tissues that have higher water content and higher ion content are better conductors. As the electrical impulse enters the body, it must first pass through the skin, which may provide a significant resistance to the electrical current. After passing through the skin, the electrical pulse enters the fat, which has very little resistance due to high water content. The skin and the fat are series circuits. The bone, muscle, blood, and nerve function as a parallel circuit. As the electrical impulse looks to leave the body, it must pass back out of the fat and the skin to complete the full circuit.